In this demonstration, we will show how to set up a conjugate heat transfer problem in the .Allsolve environment. Conjugate heat transfer is a multiphysics problem involving heat transfer in both the fluid and the solid domain. For this purpose, we have chosen a 2D Taylor-Couette flow, since the analytical solution for both velocity and temperature profiles are available. This would allow us to verify the results from our simulations. To give a brief background on the Taylor-Couette flow, it consists of two concentric cylinders with at least one of the cylinders rotating, and the gap between the concentric cylinders is filled with a viscous fluid. We are interested in simulating the steady state solution for this particular problem. Let us look at the problem in more detail. So we have chosen the problem statement from a 2016 article by D. Marinas et al. It's titled Improving a Conjugate Heat Transfer Immersed Boundary Method. It's published in the International Journal of Numerical Methods for Heat and Fluid Flow. The description of the problem is provided in detail in the left image, and the same is pictorially represented on the right image. So the geometric domain is formed by two concentric hollow cylinders. The outer blue concentric cylinder forms the fluid domain, while the inner gray hollow cylinder forms the solid domain. There are three cylinder radius of importance or of interest, which is Ri, and it's equal to 0.45, which is the inner cylinder radius, and Ro is the outer cylinder radius, which is equal to 1.8 meter, and the interface cylinder radius Rm, which is equal to 0.9 meter. It's also given that the outer cylinder radius moves with a tangential velocity of UO equal to 2 meter per second, and the outer cylinder radius is kept at a temperature of TO equal to 700 Kelvin, while the temperature of the inner cylinder surface is kept at 500 Kelvin. Furthermore, the ratio of heat conductivity between the solid and the fluid material is set to be equal to 9. We will now go to the .Allsolve environment to set up the simulation. We'll first start by creating a new project called CHT in a 2D Taylor-Couette flow. We select the cylinder icon under Create Geometry. We first define the inner cylinder, whose radius was 0.45 meters. Since it's a 2D flow, we provide a very small height of 0.05 and rotate the cylinder by 90 degrees around x-axis so that the height is in the z direction. We'll build it to see its final form. We now create the interface cylinder, whose radius was 0.9 meter. We provide the same height and rotation. Finally, we provide the input for the outer cylinder, whose radius was 1.8. We provide the same height and rotation. Once we build it, we see all the three cylinders that are created. At this moment, all the cylinders are overlapping each other. So we perform a Boolean operation called fragment all, which removes these overlappings. Finally, we perform the remove operation and select the innermost cylinder. So now we are left with the required two concentric hollow cylinders. We confirm the model changes and proceed to the next step of the simulation setup. Here we'll first define some shared expression where some of the simulation parameters which were mentioned earlier would be defined, starting with UO, which is the tangential velocity, and its value was 2 meters per second. Then we define RO, which is the outer radius, and was equal to 1.8 meter. Then we define the angular velocity variable at the outer radius, and this will be defined by UO divided by RO. We define the temperatures at the outer and inner surface. So TO would be the outer radius temperature, which was kept at 700 Kelvin. Then we define Ti, which was inner radius temperature, which was kept at 500 Kelvin. Then we define the heat conductivity ratio between solid and fluid. This was equal to 9. Now we define some materials. We require 2 materials, one for the fluid domain, one for the solid domain. For the fluid domain, we select water, and this is applied on the outer hollow cylinder. Then we select aluminium and apply it on the inner solid domain. We need to perform some modification on the material properties, since the Taylor-Couette flow is applicable for viscous flow or viscous fluids. So we change the dynamic viscosity of the water accordingly. We set this equal to the water density times 1.0. Here the 1.0 indicates the high kinematic viscosity value. In addition to this, we also need to ensure that the heat conductivity ratio between solid and fluid is equal to 9. So we take the heat conductivity of water and set the aluminium heat conductivity to be 9 times that of water. So this way the Ks by Kf value would be equal to 9. Or instead of using 9 directly, we could also use the expression we defined earlier. We see that the water and aluminium regions are automatically generated once we define the materials and selected the appropriate regions. In addition to these two regions, we also need to define some other regions where we apply the boundary conditions. We'll start with the outer surface. Then we define an inner surface. Followed by an interface surface where we apply no slip boundary condition. We also define some side walls for the fluid. Then we define some reference points at the interface region where we apply 0 reference pressure. Then we finally define a volume that includes both the fluid and the solid domain. This completes the simulation setup in this tab. So we have all the required shared expression, materials, and the physical regions for defining the interactions or the boundary conditions. We'll proceed to defining the physics. We'll first start with the laminar flow. We set the analysis type to be at steady, and we select the volume where the laminar flow physics is applicable, and select volume for this and click on apply. We'll start adding interaction. We'll start with the velocity constraint. So on the outer surface, we know that the fluid flow is moving at a tangential velocity of 2 meters per second, or UO. And we also defined the angular velocity earlier in the shared expression. So we use this information to extract the xy components of the fluid flow at the outer surface. So the x component would be angular velocity times the y coordinate, and the y component would be negative times angular velocity multiplied by the x coordinate. Since it's a 2D flow, the z component of the velocity is set to 0. We add another velocity constraint interaction. This time we select the interface surface where no slip boundary condition is applied. Hence, all the components of the velocity would be equal to 0. The last velocity constraint would be applied on the side walls of the fluid. So here we need to ensure that the z component of the velocity is 0. So we set that to 0 and disable the x and y components, as these will be calculated during the simulation on the side walls. Then we add the pressure constraint on the reference points we defined earlier. So we set this equal to 0. This completes the definition of interactions required for the laminar flow. Now we proceed to adding the heat transfer physics in the fluid domain. So to do this, we select heat fluid physics, and the region this would be applicable is water, or in our case it's fluid. We add the temperature constraint for the heat fluid physics. So we know that the outer surface temperature is kept at TO, so we select outer surface region and set the temperature constraint to TO. At this point, we have two different physics applicable on the fluid domain. So one is the laminar flow, which solves for velocity and pressure. The other is the heat fluid, which would solve for the temperature. We would need to couple these two physics together so that the interaction between these two physics is complete. To do so, we go to laminar flow and select thermal fluid interaction. Applying this thermal fluid would couple the heat fluid physics with the laminar flow. So the laminar flow together with the heat fluid would solve for all the three field variables. Now we are left with defining the physics in the solid region. So we select heat solid, and the volume that is applicable is aluminum, and we click on apply. The boundary condition is applied on the inner surface, which was kept at a temperature Ti, which was equal to 500 Kelvin. Now this completes all the necessary physics definition that is required for running our simulation. So we have heat solid in the solid domain, and laminar flow and heat fluid in the fluid domain. And we have also coupled the heat fluid and the laminar flow using the thermal fluid interaction. So we can now proceed to the last part of our simulation process. So we see here that the analysis type is steady, and also see that the three enabled physics are laminar flow, heat fluid, and heat solid. We'll proceed with creating the mesh for the geometry. To create a good uniform mesh, we go to expert settings and select default and set the scale factor to 0.1 for refinement, and we'll click on meshing. While the meshing in its process, we can set the outputs for visualization. So we'll add the pressure output in the water region or the fluid region. Then we add the velocity field in the fluid region. Then we select the temperature output and we select the fluid and solid region as targets so that we can visualize the temperature in both the fluid and the solid domain together. We see that the meshing is completed. We can preview the mesh to see how it looks. Now we can run the simulation. In the logs, we can see the progress of the simulation. We see that the simulation is completed. We can now proceed to the visualization. I'll add all the three variables for visualization. So here we see the pressure distribution. Similarly, we can also visualize the velocity profile in the fluid domain. Then lastly, we can see the temperature profile in both the fluid and the solid domain. To perform the verification with the analytical solution, we will download the VTU results and extract the temperature and velocity profile across one of the radial directions. And we have set up a Jupyter notebook to perform the verification of comparing the simulation results with the analytical solution. So we have defined the characteristics of the simulation case with the outer and inner surface temperature, with the tangential velocity and the required radius. The analytical solution is defined by v of r and t of r functions, which takes in the radius value as the input, and similarly we have extracted the simulation values from ParaView for the fluid velocity and the temperature in the fluid and the solid domain. So we'll now run the Jupyter notebook to see the comparison between the results of simulation and the analytical values. So in the top image, we see the velocity and the temperature distribution in the geometric domain, and in the below plots we can see the comparison between the simulation results and the analytical results, and we see that there is a good match between the two.